This is Lab Quest 19 titled Impulse and Momentum. In this lab, this is our setup. We have our track with our dynamics cart on the track. At this end we have a force sensor, and at this end we have the motion detector. What we're going to do is we're going to launch our cart by loading the spring-loaded plunger, pressing it in, putting it. We've got our end stop here so that the plunger, when it's released, can push off of the end stop like that. And you'll see there's an elastic band here, and the cart goes down and the band begins to stretch, and then it comes back. That's a change in momentum. That's an impulse. We're going to measure the impulse two different ways. Over here, the force sensor is going to generate a force versus time graph. And on this side, my motion detector will record the velocity of the cart throughout. So watch here on the screen. I'll show you what a sample data set looks like. There we go. Now you can see my force versus time graph as the elastic band begins to stretch, and then as it begins to come back. Here's where the string goes tight. Here's where the string goes slack. Here's my velocity versus time graph. Before the band begins to stretch, here's my initial velocity. Moving toward the sensor is a negative value. And then after it reverses direction, here's my velocity for coming back. And for the first trial, I'm going to be using the thin elastic band. Here we go. Start my data collection. And we saw the cart went forward and the elastic band changed its momentum, stopped it, and caused it to go the other direction. Okay, so we're going to do it again. And now I've got my thick elastic band connected to the cart. Let's gather our data for the thick elastic band now. Start data collection. Here we go. And there we go. We get our change in momentum for the thick elastic band measured two ways, with the force sensor and with the motion detector. So let's fill out our data table. The mass of the cart, you enter that in kilograms. Don't forget to convert grams to kilograms. And all right, we're going to take the mass of the cart on our scale here. $516 grams. My first column in my data table asks for the final velocity. So here's my velocity graph. Here's where the cart was at rest. Then the spring plunger was released and it started to move toward the sensor. Toward the sensor is the negative direction. Then the elastic began to stretch, slowing the cart down. Here's where the velocity of the cart is 0. And that corresponds to the closest approach to the sensor. You see there the value is the smallest, meaning it's closest. And of course, when the elastic is stretched the most, that's when the force is the greatest. So that agrees there. So right here is where the cart changes direction. And then the string goes slack about right here. And now it is rolling with fairly constant velocity back towards the beginning. So my final velocity then is this region right here. So I'm going to highlight that, and I'm going to go to Analyze Statistics. And now in this little statistics box, I see that my mean value for my final velocity is 0.6326 meters per second. So I'm going to use that value for my final velocity. Likewise, for my initial velocity, I'm going to highlight the region just before the band begins to stretch. And I'm going to do the same thing, get statistics for that spot. And now I see my mean value for velocity before the band begins to stretch is negative 0.766. So then I take the difference of those two, V final minus V initial, to get my third column, change in velocity, or delta V. Now the impulse under the air is the area under the curve. That's going to be the area under my force as a function of time curve. So that's this one right here. So to do that, I highlight the whole section, making sure I definitely include all parts of the graph so that it's definitely 0 on the left and definitely 0 on the right. And now this little icon right here, if you hovered over it, it will say integral. And you click on that, and there we go. That gives us the area under the curve, 0.7115 Newton seconds. So that value will go in our fourth column. In our fifth column, the amount of time of the impulse, the delta t. Look at this data table, and you see here at these times, my force is 0. So I'm just going to scroll down until I see the time where my force is no longer 0. So that's 1.14 seconds. So I'll write that down, and then I'll go to the other end of my graph and find out where it returns to 0, and that's here at 1.62 seconds. So I would take the difference of those numbers, 1.62 minus 1.14, and enter that value in my column here for delta t. Now we want to find the average force. This is a calculated value. So we see that force times time equals the area under the force as a function of time graph. If I divide both sides by delta t, I will come up with the average force. So right here, the average force, I'm going to take this value, area under the curve, and divide it by this value, delta t. And then the maximum force, we're going to compare what is the maximum force compared to the average force. This comes from the graph. So in your graph where you found the area under the curve before, now we're going to take that same region and we're going to do statistics on it, analyze statistics. And there we get our maximum value right there, 2.732 at time 1.36 seconds. And we can verify that over here in the data table. I see that 1.36 is in fact my maximum force value. So there's my value for maximum force to enter into the table right there. Then in the second table, or the third table down here, we're going to just copy this value to here, and we're going to calculate mass times delta V. So this delta V value right here will multiply times our mass in kilograms, and then refer to analysis step number 3 for how to calculate the percent difference. How different are our values for change in momentum calculated with m delta V versus change in momentum or impulse as measured by the area under the force as a function of time graph. And put your answers here for comparison.